Hello, my name is Tobias Lechler. I am a research assistant at the Institute for Factory Automation and Production Systems of the Friedrich Alexander University Erlangen-Nuremberg. Today I am glad to present you the paper Data Farming in Production Systems, a review on potentials, challenges and exemplary applications. I want to start with a short overview of the presentation. Based on a short motivation, I will present the current state of the art in simulation of production systems as well as data farming. Afterwards, the review method as well as the results will be presented. Based on the results, derived potentials as well as challenges for the use of data farming in production systems are discussed. Finally, the presentation will be concluded with a short summary and outlook. Before I will continue with the motivation of the paper, I want to inform you that every literature reference you find in the presentation refers to the list of references in the paper. Simulation studies are a common tool in the production industry to answer specific questions concerning production systems. Nonetheless, simulations leave room for further exploration of the models. As simulation models contain the behavior of a specific real entity, they can be used to answer more questions and even reveal yet undetected cause-effect relations, which lead to new insight into the real entity. Therefore, data farming was introduced as a new methodology to test nearly all possible states of a simulation model, without negative influence on the real entity, and later evaluate the generated data using data analytics and data mining methods. Data farming originated from the field of military applications, but found use in different areas such as humanitarian assistance and medical science over the last couple of years. Therefore, the aim of this paper is to analyze the potentials and challenges of data farming in production systems based on a literature review on existing applications. According to the Association of German Engineers, simulation is the representation of a system with its dynamic processes in an experimentable model with the aim of reaching findings which are transferable to reality. In the context of production systems, simulations cover the three basic components of production: products, processes and resources, short PPR. The figure above shows the usage of common simulation methods according to the PPR model as well as their level of production. Whereas finite element methods, multibody, and 3D kinematic simulations are mainly in use at the product and process level, virtual commissioning as well as material flow simulations are used more frequently on the resource level. Additionally, business process simulations are mentioned on the highest level of production. Since the usage of discrete event simulation can be traced back to the first simulation language in the early 1960s, material flow simulations in form of discrete event simulations are more widespread than newer methods such as virtual commissioning in the context of production systems. Data mining is a part of the knowledge discovery in databases process, which allows to analyze data in order to discover new insights. In the context of production systems, process data is used to optimize specific manufacturing processes. However, if data of the production system is unavailable, for example during the planning phase, simulation can be used to generate, respectively farm, the database. The figure above shows the four metaphoric steps of the data farming technique. At first, expert surveys are used to gain knowledge on how to capture important aspects about a research object. This step is called fertilize. The second step, cultivate, includes the identification of potentially important influences under certain circumstances in the planned simulation. Plant describes the transfer of the expert knowledge into simulation models and their execution. The last step, harvesting, includes the use of data analysis and data mining methods to detect new relations and therefore gain new insights. Besides the metaphoric description of the data farming process, the figure above shows the iterative data farming approach, called loop of loops. The first loop on the left side is the experiment definition loop, containing model development and rapid scenario prototyping. As the loop indicates, this is an iterative process, which leads to adjustments of the model as well as on the targeted question of the data farming study. After the first model is built up, the multi-run execution loop on the right side can be executed. There, the experiment design is defined based on the results of the experiment definition loop. Afterwards, a high-performance computing environment is used to perform the defined experiments, each of which generates datasets being stored by the data farming framework. The data is then analyzed using data analytics, data mining, and visualization techniques. Based on those results, the study can be customized by adjusting the simulation model in order to further improve the answer to the question of the data farming study. The entire process can be repeated until sufficient accuracy of the results is reached. Besides the 5 presented steps, collaboration is key for the success of the data farming study, as the expert team and simulation experts have to share their experience and expertise openly. Based on that basics about simulation of production systems and data farming, the review is done. Now to the review. In order to find relevant publications for data farming in production systems, the review methodology shown in the figure is applied. Since there are no publications with the key terms data farming and production, including different spelling, in their title at the databases Scopus, Google Scholar and IEEE Explore available, the search is extended to mentions of these search terms in the entire publications. To limit the search, publications before 1998 are excluded, since data farming was introduced in 1998 by Brandstein and Horn. The described search initially leads to 861 publications, which are further analyzed to derive potentials and challenges. The figure above shows the distribution of the review results on the different databases. Further analysis of the literature, including the removal of duplicates and filtering according their relevance concerning production systems by reading publication titles and abstracts, leads to a total of 31 relevant publications. The high number of results found in Google Scholar can be traced back to the publications considering farming in the context of agriculture. According to the number of publications including the keyword production in Scopus and IEEE Explore, data farming in the context of production in general represents a small research field so far, only comprising about 10 to 12% of the publications depending on the databases. The remainder mostly stems from military applications, since only 4 of the 31 publications are journal contributions originating from 2016 and 19. A low degree of maturity can be stated for this research topic. The 31 publications can be divided into 2 groups: fundamental data farming publications, the first 11, and data farming with application in production systems, the last 20. In the first group, almost no explicit applications are described and nearly no simulation tools are mentioned. Sanchez et al. Provide advice for the implementation of data farming studies focusing on efficient experiment design and the role of data farming in the context of big data. Tolk focuses on the integration of big data and deep learning into modeling and simulation. Furthermore, Greasley and Edwards describe data farming as part of data analytics in discrete event simulation in their review publications. Tifnam presents an approach for data farming in organization science. Nevertheless, most of the evaluations in the first group are based on military applications. Therefore, the publications by Kroll et al. And Rauch et al. Are noteworthy, since they shift from military to metallurgy applications using the software Scalarm. These applications represent the transition to the second group, which consists of data farming publications including production system applications. It is led by Feldkamp et al., who introduce a general methodology for knowledge discovery in production simulations including data farming and visual analytics. Furthermore, they present applications in exemplary manufacturing and production lines as well as other use cases. Moreover, data farming applications in the context of supply chain management exist. Xu et al. Combine data farming and clustering algorithms to analyze production sequences, whereas Sievers et al. Use data mining for the optimal dimensioning of heat pumps. The up to here mentioned publications mainly use discrete event simulation in the software plant simulation by Siemens. In addition, rare use cases in material science and factory simulation exist. Besides the presented papers and applications, you can find a short overview of related techniques such as domain randomization and knowledge discovery in general in the paper. With the rise of machine learning applications, the combination of data farming and machine learning to compose a hybrid model of a production system is a promising approach, especially if the modeling of parts of the production system is complex but real data about its behavior already exists. Therefore, the extension of real data with systematically generated synthetic data via data farming is exemplarily introduced in the context of supply chains. The second potential is the extension of present decision-making processes. Since production systems confront decision makers with complex questions over their life cycle, data farming, instead of the simulation of what-if scenarios, can be used to answer them appropriately. Through continuous improvement of computing capacities, the expansion from discrete event simulation to other simulation methods presents another potential. Due to the possible distribution of simulation runs on different computer clusters, the use of simulation methods, such as virtual commissioning as a basis for data farming, is also promising. For the application of data farming in production systems and to reach the presented potentials, collaboration is essential, as data farming in military applications has already shown. In the context of production systems, teams need production process and simulation experts as well as data analysts. The second challenge for the use of data farming in the production industry lies in precise data analysis. Since data farming aims to find new correlations, common detection methods to determine maxima or minima are insufficient. Instead, methods need to be developed to automatically determine the meaningful correlations in the multitude of possibilities data farming studies offer. Further challenges lie in the extension of the design of experiments in data farming studies to increase the performance. Therefore, streaming-capable data mining methods could be used to manipulate the experiment plan during simulation runs to accelerate the process. I want to end the presentation with a short summary and outlook. This paper presents the topic data farming in the context of production systems. Therefore, the state of the art in data farming is elaborated, followed by a review on its applications in the field of production systems. In conclusion, data farming in production systems is still at an early stage of maturity. Few pioneers transferred the data farming approach from military to production system applications, forming the foundation for future research and applications. These comprise, among others, methodologies for knowledge discovery in supply chain applications and production simulations. In order to reach the potentials of data farming, including extended decision support in complex production systems, existing methodologies, for example streaming-capable data mining methods, need to be enhanced. So I'm at the end of my presentation of the paper Data Farming in Production Systems, a review on potentials, challenges and exemplary applications. I want to say thank you for listening and have a nice 8th CIRPe Global Web Conference. Goodbye.